This week we're going to talk about sound. Here is your demonstration. Oh, there you go. Sound, as you know, is a pressure wave in the air. And we are very good at making them, and that's one of the ways we communicate. You're hearing them come out of your computer right now. Sound is a pressure wave in the air. If we were to zoom in and look at the air molecules, the way that pressure wave propagates, you would see just normally, if there were no sound, you would just see random molecules moving around. But if there were a sound wave going through, there would be regions where the density is a little low, and there would be regions where the density is really high, and then regions where the density, that's a big molecule, is really low, and then regions where it's really high based on the wavelength, and then regions where it's really low. You get the idea, okay? So these are regions of high pressure where the air density is high, regions of low pressure where it's low. If we wanted to plot it, actually the plot would kind of look like this. We would plot the pressure of the air, but not around zero, because, you know, a sound wave isn't so strong it's making little vacuums everywhere. It's really just a small perturbation in the pressure around atmospheric pressure. So we would put atmospheric pressure here and just think of little amounts where the pressure goes up and the pressure goes down, above and below atmospheric pressure. So if we were going to line this up, this would be where it's low, and then it's high here, and then it's low, and it's high, and it's low, and it's low. So it'll look kind of like this. It would just be a sinusoidal wave of pressure centered at atmospheric pressure. When you apply the laws of physics to a gas, you can derive a wave equation, that second order linear partial differential equation. You can come up with one. It's pretty tricky for sound. You got to think about how the gas molecules are conserved, and you got to think about the ideal gas law. But you can get there. Pretty nasty. So we aren't going to do that. But I can give you a little expression for the speed of sound. So the speed, you know, like any good wave, sound waves have a frequency and a wavelength, and they go at a constant speed. All that stuff applies to sound waves. So the velocity, it's the square root of something called kappa over something called rho. Or maybe that's a k, I can't tell. K. This is the elastic modulus of the air. And you say, air has an elastic modulus? Yes, it does. And this is the density of the air, right? That's a fairly small number. And if you do all that, if you plug in some numbers, sound goes at about 343 meters per second. So really fast, but not light speed fast, right? So that's why you can experience the delay of sound across a stadium or in the mountains or somewhere far away. Another way to write this, if you wanted to use a different expression, another way to derive it, is you can also go with pressure. You can see how the speed depends on pressure. So it's a square root. You got to put this constant of 1.4 in there, long story. Big P, also over rho, where this is just the pressure. And this is still the density. Right? So maybe you could imagine that if the pressure were higher of the air, you raise the air pressure, the sound goes a little bit faster. Not a lot faster, it's under the square root, but it goes a little bit faster. And all of this, these velocities also still obey the velocity of a sound wave equals the frequency times the wavelength. So you could measure the speed of sound also by measuring this wavelength at a certain frequency if you wanted to. Okay? So that's the basics of sound, just a pressure wave in the air.